The Luzon Strait opens between the northern tip of Luzon and the southern coast of Taiwan like a gate left ajar. 350 kilometers of navigable water connecting the Pacific to the South China Sea. Deep enough for carriers and submarines. Narrow enough that everything transiting it is observed by someone. USS Ross makes 23 knots on a westerly heading, threading the strait's northern approach corridor at 4:19 a.m. She has been at general quarters for 40 minutes. The People's Liberation Army Navy's positioning in the past 72 hours has been described by the intelligence community as consistent with pre-engagement preparation. And the commanding officer has not felt inclined to argue with that assessment. The ship is ready. The watch team is alert. The VLS cells are confirmed. The SPY-1D is in full active scan, and what it is seeing to the west is a YJ-18 battery on the Fujian coast, whose targeting radar has been in active mode for the past 11 minutes. At 4:19:33 a.m., the battery fires. One missile. The targeting geometry suggests a single ship engagement rather than a coordinated salvo, which the combat systems officer interprets in real time as a test of the ship's defensive posture rather than a commitment to a full engagement sequence. This interpretation will prove correct in its immediate context and irrelevant to what happens next. The Ross engages the inbound YJ-18 at 24 miles with an SM-2. The intercept is successful. The SM-2 detonates within the YJ-18's lethal radius, and the primary airframe fragments into the South China Sea approach corridor. But the YJ-18's terminal sprint phase, which it entered at 39 miles, had brought the missile to approximately Mach 2.8 at the time of intercept. And at that velocity, the warhead section, structurally separated from the propulsion section by the SM-2's rod warhead detonation, continues forward on a ballistic arc. The warhead section does not detonate. Its fusing system, which requires a specific contact deceleration signature to arm and fire, has not received that signature from a mid-air fragmentation event. The 300-kilogram mass of shaped charge and steel casing arrives at the Ross's starboard side at Mach 1.4 at 4:19:51 a.m. It strikes the hull plating at frame 68, starboard side at the waterline, not below, at. The waterline strike is the most structurally damaging geometry for an Arleigh Burke-class hull because it applies the impact loading simultaneously to the hull plating and to the hull structure in the transition zone between the above-water and below-water frames. The zone where the designer's assumptions about wave loading and shock loading overlap, and where neither set of assumptions was written for a Mach 1.4 impact from a 300-kilogram object. The warhead section punches through the 19mm HY-80 hull plating, and the internal structural frame at frame 68 travels approximately 2.1 meters into the ship's interior before the secondary structural frame at frame 70 stops it and comes to rest in the starboard main engine room. The starboard main engine room, one of two spaces on the ship that contains a running LM-2500 gas turbine driving the starboard propeller shaft. The LM-2500 that occupied that space has been running at 20,000 revolutions per minute, producing approximately 25,000 shaft horsepower, consuming JP5 at a rate of approximately 3,400 gallons per hour, and maintaining an exhaust temperature at the turbine exit of approximately 540 degrees Celsius. The warhead section does not detonate on impact with the secondary frame. The fusing system still has not received the contact deceleration it needs, but the warhead section's impact with the secondary frame has fractured the starboard engine room's JP5 fuel supply line at its connection to the turbine fuel control unit. The fracture is not a clean break. It is a partial shear that leaves the line partially attached and partially open, with fuel at operating pressure of 65 pounds per square inch spraying from the fracture point in an atomized mist. The atomized JP5 mist in a 540-degree exhaust environment ignites within 0.4 seconds. The fire in the starboard main engine room begins at 4:19:56 a.m., 5 seconds after the warhead section's impact. The LM-2500 gas turbine's automatic protection system detects the fire via its fire detection sensors and commands an emergency shutdown at 4:19:58 a.m. The turbine begins spooling down. The starboard shaft loses power. The ship, which has been at 23 knots, begins to decelerate on the starboard shaft, while the port shaft continues at operating power. The asymmetric thrust begins a slow yaw to starboard that the helmsman counters with rudder input. The ship is not out of control, but the machinery space that is now burning is the space the CO2 fixed suppression system is designed to address. And activating the CO2 system requires completing the turbine shutdown. You cannot discharge CO2 into a space with a running turbine because the CO2 concentration required to suppress the fire also removes the combustion air the turbine needs to operate. And a running turbine in a CO2 atmosphere creates a dangerous partial combustion condition that the safety doctrine absolutely prohibits. The turbine is not yet stopped. It takes approximately 90 seconds for an emergency shutdown LM-2500 to spool from 20,000 revolutions per minute to a stop. During those 90 seconds, the fire in the starboard main engine room is burning without CO2 suppression, growing in the presence of fuel from the fractured supply line and the residual heat of the turbine exhaust. The space has a pre-installed AFFF foam system that does not require the turbine to be stopped. AFFF can be activated immediately. But the AFFF system in the starboard main engine room has one operational constraint that the CO2 system does not. The AFFF foam supply line runs through the engine room bulkhead via a fitting that has been deformed by the warhead section's impact on the secondary frame. The fitting is not severed, but the deformation has reduced the AFFF line's internal diameter by approximately 40%, which limits the foam flow rate to a level that the fire suppression engineers would characterize as insufficient for a fuel-fed fire in a space of this size and heat load. The Ross's fire response team cannot use CO2 because the turbine is still running. They cannot use AFFF effectively because the supply line is compromised. What they have is personnel entry in SCBA gear with 1.5-inch hose lines connected to the fire main, fire boundary establishment to contain the fire to the engine room, and time. Time is the one thing they do not have in large quantity. Because the JP5 fuel supply line fracture is still open, the fuel is still spraying, and a fuel-fed fire in an engineering space with structural steel temperatures rising toward their thermal failure points is a fire with an agenda of its own. In DC Central, the chief engineer reads the damage picture at 4:20:08 a.m., 12 seconds after the impact, 2 seconds after the fire detection alarm. He has in front of him one of the most constrained damage control situations an engineering officer can face. A fuel-fed fire in the main engine room, turbine still running, CO2 unavailable, AFFF compromised, and a ship that needs to be maneuvering for its own defense because the Fujian battery has not been confirmed to have stood down. If the port engine is also taken offline for any reason, if the fire spreads to the port engine room, if the port fuel supply is compromised in sympathy, if the asymmetric thrust maneuver overloads the port turbine, the ship loses propulsion entirely and becomes a stationary target in the middle of a strait where the adversary has already demonstrated willingness to engage. He cannot stop the starboard turbine faster than its own momentum will stop it. He cannot use CO2 until it stops. He cannot use AFFF effectively because of the compromised line. But he has one option that exists in the damage control library as a recognized emergency procedure. It is not standard, it is not first choice, and it is not comfortable. Called the ventilation boundary approach for confined machinery space fires. The ventilation boundary approach works on the physics of fire suppression that does not require a suppression agent. A fire requires three things: fuel, heat, and oxidizer. If you can reduce the oxidizer concentration in the burning space below approximately 15%, normal atmosphere is 21% oxygen. The fire cannot sustain combustion regardless of how much fuel and heat are present. The CO2 system achieves this by flooding the space with CO2, which displaces the oxygen. An alternative approach, applicable only in specific geometries, is to seal the space's ventilation inlets and outlets. Not with CO2, not with AFFF, but physically, with fire boundary material, and allow the fire itself to consume the available oxygen in the sealed space until the concentration drops below 15%. The fire suppresses itself. The limitation of this approach is time and thermal loading. The fire consumes itself slowly because the oxygen depletion is gradual. And during the depletion period, the fire continues burning, continues heating the structural steel, continues risking thermal failure of the bulkheads and overheads in a space with unlimited fuel supply, which the fractured JP5 line provides. The fire cannot consume more oxygen than it is feeding back in through the fractional re-entry of combustion products. The ventilation boundary approach only works if the fuel supply is also interrupted. The fractured JP5 line must be closed. Closing the fractured JP5 line requires someone to get into the starboard main engine room. The space is on fire. The turbine is still running. It will stop in approximately 75 more seconds from the point the chief engineer is assessing the situation. After the turbine stops, CO2 becomes available. But CO2 takes 30 seconds to achieve suppression concentration after activation. And the fire has now been burning for 25 seconds, and the structural steel in the area of the fuel fracture is heating. The window for a personnel entry to close the fuel supply before the thermal environment becomes unsurvivable is approximately now. The chief engineer calls the lead machinist's mate. Repair party 2. Starboard main engine room port access. The fuel supply line to the turbine fuel control unit has fractured at the connection fitting. I need the manual fuel shutoff valve upstream of the fracture closed. The valve is on the port side of the turbine fuel skid, marked F-STBD-1. Yellow handle, quarter turn ball valve. You have 60 seconds from now before the turbine stops and I can activate CO2. If the fuel valve is closed before the turbine stops, I can activate CO2 immediately on shutdown confirmation. If it is not closed, I will activate CO2 anyway, and the fuel line will continue feeding the fire through the suppression agent. Move now. The lead machinist's mate and one damage controlman enter the starboard main engine room at 4:20:44 a.m. in full SCBA gear with silver proximity suits. Not full fire entry suits, but the proximity suits provide sufficient thermal protection for a 60-second directed entry in a space where the fire is concentrated at the fuel skid location and has not yet spread to a full space involvement. The access point is the port access scuttle, which is on the opposite side of the space from the fire. They have 1.5 inches of thermal and SCBA protection between them and a burning turbine engine room. The visibility in the space is approximately 3 feet in the direction of the fire. The combustion products have filled the overhead volume and are descending. Below the combustion layer, at floor level, the air is marginally clearer. Both crew members immediately drop to their hands and knees and navigate along the deck by the layout they know from drill. Port access, 3 meters to the turbine service walkway. Walkway leads to the fuel skid on the starboard side of the turbine housing. The lead machinist's mate can hear the turbine, still running, audible even through the SCBA mask, as a high-frequency mechanical scream that is descending in pitch as the spool down continues. The thermal radiation from the direction of the fire is intense, not hot enough to ignite the proximity suit at the current range of 4 meters, but hot enough to feel as a directional pressure on the left side of the body. The fuel skid is visible through the smoke at a range of 2 meters. identifiable by the yellow handle on the FSTBD1 valve, which is catching the emergency red lighting. The lead machinist's mate reaches it at 4:21:09 a.m., 25 seconds into the entry. He puts his hand on the yellow handle. The valve is a quarter-turn ball valve designed to rotate 90 degrees from open to closed. In the normal position, open, the handle is parallel to the pipe. Closed position is perpendicular. He rotates it clockwise. It moves. A quarter-turn ball valve takes approximately 1 second to close fully. The fuel spray from the fractured line downstream of the valve stops instantly as the upstream pressure is cut. The fire does not stop instantly. There is residual fuel on the engine room deck and surfaces still burning, but the sustained fuel supply, the 3,400 gallons per hour JP5 flow that was maintaining the fire's intensity, is gone. The fire begins to run on what it has, which is enough to keep burning, but not enough to grow. At 4:21:23 a.m., the turbine spool-down monitoring panel in DC Central registers rotational speed 0 on the starboard shaft. The turbine has stopped. The chief engineer activates the CO2 fixed suppression system for the starboard main engine room at 4:21:26 a.m., 3 seconds after the turbine stops, which is the minimum safe interval the doctrine requires. The CO2 flood begins. The oxygen concentration in the starboard engine room begins dropping. The fire, running on residual fuel without a continuous supply, finds its oxidizer declining. The fire in the starboard main engine room is suppressed at 4:22:41 a.m. 80 seconds after CO2 activation. It takes 80 seconds rather than the nominal 30 because the residual fuel on the deck and surfaces is acting as a sustained fuel source that slows the oxygen depletion. The fire watch confirms suppression via the thermal camera feed in DC Central at 4:22:41 a.m. The 2 personnel who entered the space exit through the port access scuttle at 4:22:15 a.m. before the CO2 flood begins in earnest. Their combined entry and exit time is 91 seconds. Both crew members are assessed by the medical officer at 4:28 a.m. The lead machinist's mate has minor thermal contact burns on his right forearm, where the proximity suit sleeve shifted during the crawl along the engine room deck, exposing a small area of skin to the radiant heat environment. The burns are first degree, across an area approximately 8 centimeters by 4 centimeters. He did not report the burns during the entry or exit. He reported them at the medical assessment when the sleeve was rolled back. The medical officer treats the burns and clears him for watch standing. He is back at his station at 4:41 a.m. The starboard main engine room is sealed under CO2 for the post-suppression reflash watch period. 30 minutes minimum before any personnel re-entry. During this period, the ship operates on the port turbine only, at reduced speed. The port turbine carries the ship at 14 knots. At 14 knots, the time to transit clear of the Luzon Strait is approximately 2 hours and 20 minutes. The commanding officer orders the transit to continue. The Fujian battery has not retargeted. The radar mode returned to surveillance mode at 4:21:17 a.m., 26 seconds after the Ross's ship speed began dropping. The battery is watching but not preparing. The commanding officer interprets this as consistent with the original assessment. A test engagement, not a commitment. He is not certain. He maintains the transit heading. At 4:52 a.m., during the reflash watch period, the damage assessment team completes its external survey of the starboard hull at frame 68. The hull breach is a roughly elliptical penetration, approximately 55 centimeters by 40 centimeters, centered at the waterline. Below waterline, flooding through the breach is occurring at approximately 25 gallons per minute, as each wave interaction temporarily submerges the lower portion of the penetration. A manageable rate for the P250 pump that has been running since the damage assessment team discovered the waterline position of the breach at 4:36 a.m. The warhead section itself is still inside the ship. at rest against the secondary frame at frame 70 in the starboard engine room, which remains sealed under CO2. The warhead section's fusing system indicator is not accessible for inspection through the CO2 environment. EOD assets have been requested from Okinawa. They will arrive in approximately 4 hours. The structural frame at frame 68 has been stressed by the penetration event and will require assessment before the starboard shaft can be reloaded. A propulsion plant restart in a structurally compromised space with an unexploded warhead section present is not something the chief engineer will authorize until EOD has assessed the ordnance and the structural engineers have assessed the frame. Both will happen in Okinawa, not at sea. At 5:02 a.m., 22 minutes after suppression confirmation, the machinist's mate opens the engine room access on the port side for the re-entry safety check. The space has CO2 atmosphere. The entry team wears SCBA. The thermal camera confirms no visible hotspots. The space is cleared for reflash watch at 5:09 a.m. The warhead section is photographed from a distance. Its fusing indicator reads safe on the external panel, consistent with a fuse that has not achieved the required impact signature. This assessment is preliminary, non-binding, and will be confirmed by EOD. The Ross exits the Luzon Strait at 7:04 a.m. at 14 knots. Port turbine only, starboard engine room sealed and under reflash watch. Hull breach at frame 68, receiving P250, dewatering at a rate that is stabilized at 22 gallons per minute. Warhead section secured with structural foam injected around it at 5:47 a.m. to prevent movement during transit. The EOD team arrives by helicopter at 8:51 a.m. from Okinawa. They assess the warhead section in 11 minutes. The fusing system is confirmed in the unarmed state. They secure the warhead with additional restraint materials and recommend yard removal under controlled conditions. The ship continues to Okinawa. The accounting at Okinawa takes place over 3 days of inspection. The starboard engine room has sustained fire damage primarily to the fuel system and the turbine fuel control unit. The LM2500 itself is assessed as potentially serviceable after a depot-level inspection of its turbine section and combustion system. The inspection will take 8 weeks. The ship will be without starboard propulsion for that period. The hull breach at frame 68 requires a yard repair, steel insert plate, frame reinforcement, new penetration protection fittings. The warhead section is removed on day 2 by the EOD yard team using controlled procedures. The space it occupied for 43 hours of transit and anchorage is cleaned, inspected, and assessed structurally. The fuel supply valve, the yellow-handled quarter-turn ball valve marked FSTBD1 that was closed by hand in a burning engine room at 4:21:09 a.m., is still in the closed position when the yard team opens the engine room for the initial inspection. It has been in the closed position since the machinist's mate turned it. The yard technician who documents the space inventory notes the valve position in his inspection log and adds a remark: "Position as found. Closed by crew during emergency." He asks if the valve should be reset to its operational position. The engineering watch officer tells him yes, once the fuel system inspection is complete. The valve is reset on day 3. Nothing was written about the valve on the wall. Nothing was written on a laminated card. There is no record of the specific decision the chief engineer made at 4:20:08 a.m. The decision to send 2 people into a burning engine room with proximity suits and 60 seconds to close a valve before a CO2 system became available. That decision exists in the engineering watch log as a single entry. Ordered R/P2 entry, starboard ER for fuel isolation, F-STBD-1 valve. The outcome: fire suppressed, turbine stopped, CO2 activated, is documented across 3 subsequent log entries. The reasoning behind the decision: the risk assessment the chief engineer performed in 12 seconds of reading a status board and making a call that required 2 people to enter a burning space, is not in any log. It is in the professional memory of everyone who was in DC Central at 4:20:08 a.m. and watched it happen. That is where engineering decisions at that speed and at that consequence level are stored. Not in the logs. In the people. 1YJ-18 warhead section, 300 kilograms, impacted the starboard hull at frame 68 at the waterline at Mach 1.4. Starboard LM-2500 gas turbine emergency shutdown, activated at 4:19:58 a.m. JP5 fuel supply line fractured at turbine fuel control unit. Fire began at 4:19:56 a.m. CO2 suppression unavailable during turbine spool down period of approximately 90 seconds. AFFF supply line compromised at 40% flow reduction by frame deformation. 2 personnel entered the burning engine room in proximity suits at 4:20:44 a.m. Manual fuel shutoff valve F-STBD-1 closed at 4:21:09 a.m. Fuel supply to fire interrupted. Turbine stopped at 4:21:23 a.m. CO2 activated at 4:21:26 a.m. Fire suppressed at 4:22:41 a.m. Combined entry and exit time for fuel isolation team, 91 seconds. 1 minor thermal burn reported. EOD team confirmed warhead fuse in unarmed state at 8:51 a.m. Starboard engine room offline pending depot inspection. Ship status operational. The post-event analysis circulated within the naval engineering community identified the 12-second decision interval between damage assessment and personnel entry order as the event's defining moment. The chief engineer had 12 seconds to determine that. The CO2 system was unavailable. The AFFF was compromised. The fuel line was the fire's continuous source. The valve was accessible, and the entry was survivable with the available protective equipment in the available time window before the thermal environment became unsurvivable. He got all 5 of those assessments correct. He was asked in the formal debrief how he processed that much information in 12 seconds. He said it was not 12 seconds of processing. It was 12 seconds of confirming what 14 years of machinery space experience had already told him before the alarm started. He said a fire in a main engine room with a running turbine and a fractured fuel line has only one path to suppression that does not require the turbine to stop first. And that path is the manual fuel shutoff. He said he knew where the valve was because he had been in that engine room enough times to know where everything was. He was asked if the entry team had been at risk. He said yes. He was asked if he would make the same decision again. He said he would, because the alternative was a fire with a continuous fuel supply burning in the main engine room for 90 seconds until the turbine stopped. And 90 seconds of a fuel-fed engine room fire produces structural steel temperatures that make post-suppression use of that space a longer-term problem than the entry risk was a short-term problem. He paused. Then he said, "The 2 people who went in knew what they were doing. That matters. You cannot send people into a burning engine room and have them close the right valve in 60 seconds unless they know the space. They knew the space. That is not something that happens in an emergency. That is something that happens in every watch, every drill, every time someone walks through an engineering space and pays attention to what is in it. The emergency is where that knowledge gets used. The knowledge itself comes from everywhere else.